questions on exam material, on the course material before you take the exam. So, any questions? One of you came up to me after class last time and said there was a question on the practice exam for which the answer was wrong, and I believe that was not the case, that the answer wasn't wrong, but I can't remember exactly which question it was. And so would after class, would the person who said there was an answer on the practice exam that was wrong, please come up to me and show me which question it was, and let's discuss whether the answer given was right or not. I guess I'll wait a minute officially till my watch says it's 9:30. My watch is within a half minute of being accurate. So right after class, the exam is open. And from then till next Monday at 11:55 p.m., you are not to talk to each other about any course material. Okay? No communication among you. However, you're welcome to have any use any other material. It's completely open, anything you can look up. The pledge that you have to check is very vague. I mean, very general. It says I neither will give nor receive aid. But in the instructions at the beginning at the top of the exam, it lays out what that means, and it says exactly what I just said. Namely, when you're signing that pledge, you are saying that you have not received information from another individual during the time of the exam, nor given it. Okay? The exam consists of 84 questions. Sakai is fairly nasty in its restrictions on how you can make a question. So there are a whole lot of questions that, as I made them, there was a statement about a situation, and then it said, here are 5 statements. For each of them, say whether it's true or false, for example. Sakai doesn't allow you to do that. What you have to do is make a statement. I mean, each question has to have a single answer choice. You can't say the first statement is the first statement about the situation is true or false, and the next one is true or false, the next one. You have to set that as five questions, separate questions. So the way we've set it up to make it not too expensive is the questions will have the form. It says questions, 23 to 27 are on this situation, and then it gives a situation, and it gives the first answer. It says, and for each, say whether it's true or false. And then for the first question, it will say whatever the statement you have to say true or false is, and then you say true or false. Then you go to the next question, the next thing that you have to say true or false about the same one, and it does not repeat the situation. I want you to understand that, the situation is given in the first of those, and all the rest are just the statements that you need to say true or false. Okay, or whatever the collection of possible answers are for that. Is that clear? If you have any questions of interpretation, I want you to be able to get them to be answered right away, right? Because my email box, I will try to keep up with my email, but because my email box gets unbelievably cluttered, I sometimes don't answer right away, and I want you to have the answer right away, and therefore, if you have questions of interpretation, please pose them by telephone, okay? And basically, during working hours, 8:30 to 5 today or tomorrow or Monday, on the work days, call me at my office number, 919-590-6085. I will attempt to keep up with voicemail, but if you don't get an answer within an hour of the time you call again. Okay? I would prefer not to receive calls later than 9 o'clock in the evening when I'm home, or earlier than 8 on weekend days and 7:30 on weekdays. And my home phone number is 919-929-3641. And if you are calling that number, and then if it is not immediately answered and it goes to voicemail, say your name and say, I am a Comp 576 student. And then we will pick up, okay? If I'm there. If I'm not there, then ask your question and I'll give me the number I should call back, and I will call you back. I've been careful about the exam. All three of the LAs have read the questions. I have checked the exam as it was about to be put in. The button that says, make it available, was pushed. I don't know of any problems at the moment that are in there. Okay, I hope it will be completely clear. But if the system doesn't work, or if there's questions of interpretation, or if you find a question that you think is just plain has an error in it, okay? Whether it's a typographical error or an error of clarity or what have you, please call me and tell me. I will not only tell you what the right interpretation is, but you will be doing a service to everybody else, because I will be posting via the Sakai announcements mechanism, which causes an email to be sent to each registered student, any corrections that need to be put. And so well before you're ready to submit the exam, please make sure you've looked at your email or looked at the announcements on Sakai to see whether there are any corrections put in. As it says here, okay, the way the exam is set up, there are 84 questions. Each one is worth 1 point. So a raw score will be 82 out of 84, for example. I hope you get that kind of I'd love to see some 84 out of 84s, right? Anyway, once the exam is closed, the next morning or the next day, we will cause the broadcast of the right answers and of your respective raw scores. However, be aware that the raw scores are raw scores and are not your final score. Because if I, for some reason or another, decide that a particular question is, I don't know, too hard or turned out to be somewhat unclear, I may lower the value for that particular question. So, instead of being worth 1 point, it might be worth half a point. Okay? And I will not be able to know that until I get the histogram of all the grades on all the questions. And so while I don't curve the scores, I do look at each question and try to understand if there's a large fraction of you who did badly on their question, why that might be. And if I judge that that was some legitimate reason, I will lower the point score for that, and you'll end up with a final score once that's happened. Okay, so I mean, if I, for example, lowered 2 questions from one point to a half point, then instead the exam score would be out of 83 rather than out of 84, right? And I take those ratios as a percent, okay? And my general practice is that 85 to 100%, you should understand as an A. Basically 95 to 100 as A plus, and 90 to 95 as a A, and 85 to 90 as an A minus, and 70 to 85% as a B. Again, think of it as divided into 5% scores, right? And 60 to 70% as a C, divided roughly into thirds, to C minus C, C plus, C minus, and C. Sorry, C plus, C, and C minus. And 50 to 60% as a D, and less than 50% as an F. Okay, I hope I'm not seeing very many of the lower ones, but that'll give you an idea of, from the from the score that you get, where you are letter grade wise. I have graded 2 of the homeworks, 4 and 6, and we'll shortly be doing 5. 4 was intended to be easy, and very, very many of you did very well on that. 6 was was harder, and still many of you did quite well, but some of you didn't do as well. I've gotten email from a few of you in response to my grading, and I haven't had time to deal with what's said on the email, but I will. But in any case, as a result of the 3 homework grades, 4, 5, and 6, and the exam grade, you can look up on the original, what I call poop sheet, the original information sheet for the course, what the weights are of the homeworks and of the exam scores, and you can calculate what your likely grade level is at this point. If you are impressed that you're not doing as well as you wished, then I very much invite you to come to office hours and get tutoring, if you will. I'm happy to try to improve your your understanding and thus your grade. I remind you that the midterm exam serves two purposes. First of all, it gives you an indication of what, how well you're understanding. And secondly, it provides input to the final grade. However, I remind you that the final will be, if you get a better grade on the final, the midterm grade will be ignored. Okay? And so if you find yourself not understanding as well as you thought, and that was shown by a lowish grade on the midterm, all is not lost. You can truly get that ignored by learning the material better and then doing better, getting a better grade on the final. As you may remember, if the grade on the final is worse than the midterm, then I simply unweighted average the midterm and the final grade, final exam grade, to produce the overall exam grade. Any questions on all that? Yeah.
Can I ask a question about material?
By all means.
On the 2018 midterm exam, could you move the number 20?
Want me to, which, on the practice exam?
Yes.
Okay, hold on, let me find it.
It's the other one.
Say again?
It's the other practice exam.
The other?
There was another one that's...
Oh, you're not asking about the one that I distributed for this practice, but one of the earlier ones.
Yes.
Okay, then I will get back to that. I haven't looked at that for a long time. While you're on Zoom. Okay, which exam are we talking about?
The midterm exam 2018.
This one here?
Yeah. Question 20.
This is the one, right?
Yeah.
Which question?
Number 20.
Okay, I need to get this onto Zoom. Give me a moment. All right. Go ahead. What's the question?
Could you just go over it?
All right. Okay, so A is a not necessarily square matrix. What we know about a not necessarily square matrix, and in fact about any matrix, is that A can be written as a rotation in the input space, a diagonal matrix of the same, if this is M by N, This is an n by n rotation. This is a m by n diagonal-ish matrix, and this is m by n. All right? Rotation matrices have orthogonal unit columns, right? And as a result, ST can also be written as inverse. A diagonal m by n matrix, I'll draw it three ways, depending on whether m is bigger than n or m is smaller than n or it's equal to n, has elements where I equals j, and that means if it was this size, this is always the same size as this is, the non-zero elements are along there. If it's square, they're there, and if it's rectangular that way, it's there. Okay, so far so good? Okay, so the B, the C, and the D are are respectively a rotation matrix, a diagonal matrix, and another rotation matrix. So I've just said the second item is true. B is a rotation matrix, that is to say, and it's an m by m one. I've just written that there. D is an n let's see. There's a problem there, isn't there? D should be, yeah, that's right, sorry. D is indeed an m by, I'm confused. Let's see. So A, statement 2 is correct. B is a rotation matrix of size m, and a rotation matrix in m space, and D is what is a rotation in D. Let me just put in something there so as to not confuse this D and that D. Okay. Let's see, the second one. Basically says that C is a diagonal matrix, and that's true. The fourth one, C is m by n. Yep, it is. I mean, this gamma is m by n. Two rotations and some directional scalings with possibly some reflections. Yeah. The point is that if any one of these entries, these diagonal entries, some dimensions are being thrown away, possibly, and those correspond to the zero eigenvector, the zero diagonal elements. A zero diagonal element, when you multiply something by zero, if it had a coefficient a sub I, and now it has 0 times a sub I, it no longer has a value other than 0. Its value is 0. Okay. If the multiplier that's on the diagonal, which is a stretch factor, is positive, then you're either, if it's greater than 1, you're expanding by that factor. If it's less than 1, you're compressing. But if it's negative, it means that whatever the component in that direction was, its sense is opposite, right? If you multiply by -3, that means that if you had an AI and now you have minus 3 AI in that, that says whatever direction it was before, it's swapped, and that's reflection. Okay? I'm worried about the first. Oh yeah, okay. So the problem with the first one is that B is M by M and not N by N. And likewise D is. That swaps the which is the N and which is the M. Right? Does that do it for you? Any other questions? Yep.
Are the columns orthonormal here because it's a linear operator, or is that something?
No. Let's be careful. You can. Okay, I'm going to answer in two parts. I'm going to answer in terms of eigenvectors. Okay. A is a matrix. Matrices are a representation of a linear operator, and not necessarily shift invariant operator, but a linear operator. For every linear operator on discrete data, there is a matrix, A, that you give it an input vector and it produces an output vector. Right? A takes, when applied, okay, so this is an M by N. When applied to an N vector, yields an M vector, W, which is M by 1. Right? It maps vectors to vectors. Vectors in N space into vectors in M space. Right? So if you have a three-dimensional space and you have a vector up to some point in that three-dimensional space, you put that vector in, and if, for example, M equals 2 and N equals 3, then this maps this vector to some other vector. So this will be V, and this will be W. All right, linear operators do that. Okay, if M equals N, it maps a point in a vector in 3 space to a vector in 3 space, right? And that's true for linear operators. If A is symmetric, it doesn't make any sense to talk about symmetric unless M equals N. Right? Symmetric meaning A sub ij equals A sub ji for all I not equal to j. Right? A equals A transpose. Right? That's symmetric. If A is symmetric, then you know that the as in that this is the inverse of that rotation. Which means that there's some axis in a rotation is a thing that has some axis in the space that all the points rotate about. That's what rotations are. They always have an axis. And then there's a question of what the angle is of rotation about that axis, right? You have an axis here in 3 space, you want a rotation, it's going to have an axis, and the points over here are going to rotate about that axis. Right? The axis for a particular rotation and its inverse is the same, right? If you have an axis in space and you rotate by theta here, you rotate about the same axis by minus theta, it turns the thing back to where it came from, right? And so everything is hunky-dory. These two axes are the same, and all that's happened is that you've expanded in some of the directions. The point here is that if A comes from a shift invariant operator, then A will be symmetric. Okay, so the shift invariance business comes from the particular case where the vectors are images, right? Because an operator, in this course, image computing is what the topic is. And so we're talking about operator T on images. And that shift invariance involves, not only sort of along the vector, but in an image you have not only directions this way, but directions that way, for example, in 2D. And shift invariant has to do with what happens when those points shift, when you translate the image. That's what shift invariant means. When you shift the image, you translate the image. So you have these operators that are shift invariant, and when they're expressed, if you have an n by n image, that relates to an n squared vector, right? A vector that has n squared elements, right? And so the matrix that corresponds to this shift invariant operator would be an n squared by n squared operator, because it takes an image in and it produces an image out. So for an n by n, for an operator T on an n by n image, A is n squared by n squared. And what I've told you, actually many times, and happy to repeat it, for shift invariant operators, n squared by, for shift invariant operators, that n squared by n squared matrix is symmetric. And if it's symmetric, then, what I said here, R and S are the same rotation, or another way of putting it is the S transpose is the inverse rotation to R. It's about the same axis, but by the negative angle around it, angle of rotation. That do it?
So are the columns always going to be orthonormal?
Okay. sometimes, instead of thinking of it geometrically as rotations and stretchings, we think of it algebraically as a matrix. Quite reasonably can be thought of as a collection of columns. Just n vectors. The first n vector, the second n vector, up to the nth n vector. Which can also be understood this way. Okay. In terms of rows. I need another letter. O, Q, 1, Q, 2. And if you think about what happens when you do the multiplication by a matrix, the first element of the result is simply the dot product of this with this vector. Okay, so this is V. Q1 dot V. The first element of that matrix. And Q2 dot V is the next one. Okay, so matrix multiplication is just a collection of successive dot products of the rows of the matrix with the input. Rotation matrices have the property that these rows are orthogonal. Sorry, these columns are orthogonal. V1, what do I have here? U1 is orthogonal to U2 and to U3 and to UN, and U2 is orthogonal to U1 and U3 and up to UN and so on. They're all U sub I dot U sub J is 0 if I is not equal to J. And that orthogonality allows you to take any vector and dot it with a U sub I and to get the coefficient A sub I. Depends on the orthogonality for the dot product rule to apply. Well, so I can talk about, let me just make sure we're talking the same term. This is U, and this is U. Okay, for a orthogonal matrix, its transpose is equal to itself. Right? Which means its rows are equal to its columns. This guy is just the eigenvectors. Okay. So the rotations are just telling you that the unit vectors, that after the application of R, or R inverse, that the eigenvectors of A have been rotated into cardinal coordinates, into E1, into 1, 0, 0, and 0, 0, 1, and 0, 1, 0, all zeros, and so on, right? whereupon the diagonal matrix simply multiplies the first one by the first diagonal element, the second one by the second diagonal element, and the third one by the third diagonal element in stretching. And then the whole business is rotated back. So the connection is that this rotation matrix is just the list of eigenvectors. Of A. It all hangs together. But it depends on A being symmetric for all this to happen. If A is not symmetric, you still have this relation. It's always true for any matrix, and in particular for any square matrix, that that's true, but no longer will R and S be the same. And so you need a symmetric matrix, and shift invariant operators yield A being a symmetric matrix. And therefore, for shift invariant operators, the eigenimages are orthogonal. But if I don't tell you that it's shift invariant, then you can't know that the eigenvectors are orthogonal. So R and the list of eigenvectors is the same matrix. Emma, have I left anything out? More questions? I know this, for some of you, this is the first time you've seriously got into what matrices are. One of the major objectives in this course is for you to come out understanding what they are. More questions? Okay, so I'm going to now move on to new material. We've been talking about interpolation. I remind you that the situation is that we have images of pixels. And often we need to be able to figure out what the value of the image is at places other than one of the pixel centers. The values of the image in a discrete image are the values of at those pixel centers. And now there's a new place, and we have to figure out a value here. And I told you that a very common reason for doing that is that we often have to do geometric transformations like rotation, or scaling, or translation. And if I translate this image here by half a pixel, then the new pixel centers are not going to be where the old pixel centers are, for example. And I need to compute where in this shifted image, shifted by half a pixel, the values of its pixel centers are, which were places in the old image that weren't at pixel centers. Right? So we have to be able to interpolate. And the same goes if I rotate an image, or if I stretch an image, so-called scale an image, or if I do a more complicated deformation, where some places in the images are compressed and some are stretched, and some places in the image may be rotated by such and such an amount, and other images, other places in the image are rotated by a different angle, and so on, right? Deformations are just sort of sections of each section of the image can be understood in terms of a local set of orthogonal stretches, rotation, and translations. But if different places in the image, it's not uniform across the image. So some places are stretched more, some places in the image are stretched less, some rotated by a certain amount, some rotated by a different amount, and so on. You get deformations. Okay, and deformations, again, take places that the new pixels after the deformation, if they're going to be, I'm not going to map from places in the original image that were pixel centers. And so if we're going to figure out what in the new image, it's at its pixel centers where what the value should be if this guy mapped onto a pixel center after this geometric operation, then we're going to have to be able to figure out what the value at the x is and transfer it over into the new pixel place. Yeah.
Determines where our pixel
What is what?
What determines where our pixel centers are?
Well, you have a grid. I mean, the pixels are always set up in a grid. So I'm just going to make a little 4x4 one. If you've decided you're going to have a 4x4 image, the centers are those places. Right? I mean, what you're doing is you're dividing a particular part of space equally and go into these little squares, or in general rectangles, right? If it's different number of pixels in one direction than in the other. And we always understand the intensities to be the intensity at that location. Normally, as I expressed in the earlier part, value at that location where the value is actually the average of the intensities in some finer sampling within that whole box. And the same goes in 3D, right? And I have little cubes, little mini cubes. Questions? More? Okay. So what we said last time was that essentially because any interpolation operation that we want to call an interpolation is going to be linear in the pixel values, and is going to be shift invariant, then it will have a kernel associated with it, a convolution. It is a linear shift invariant operator, which always, for any linear shift invariant operator, it can be written as a convolution, and there is a convolution kernel. And so, and likewise, there's the Fourier transform of the convolution kernel, that is to say, the convolution operation understood as multiplication in the frequency domain. And we can understand the interpolation operation in terms of its kernel, or equivalently in terms of the transfer function that it applies. And so we have a frequency domain, and the image we can think of it as a magnitude and a phase. The image has a magnitude and phase function. Or we can think of the magnitude and phase as at every frequency there being a complex coefficient. We saw that that's an equivalent way of understanding it, a complex coefficient, yeah. And what we would like is that the interpolation doesn't change. The ideal thing is that it shouldn't mess up the image. The interpolation operator shouldn't somehow lose information. It should just extract information that was just there. Which is to say, we want the interpolator to not change phases, and to multiply magnitudes by 1. That's what we'd really like, right? And I remind you that if you have a discrete image, this thing goes from -0.5 to +0.5 in frequency. N over 2 over n on the right side, which is 1/2. On the other end, it's -n over 2 over n, but for 1 over n. So we would like, in this range, -0.5 to +0.5 of frequency. Rho is always some integer divided by n, right? Where the integer is between -n over 2 plus 1 and +n over 2. This is all in one dimension, but happens in both dimensions. Okay, so we would like, ideally, this guy to be like so. And what we saw for linear interpolation is that it's not like so. Because linear interpolation involves convolution with a triangle, which is since a triangle is the convolution of two rects, and in the frequency domain, a rect is a sinc function. Applying the triangle is in the frequency domain here. This T is frequency. Is multiplying not by 1 everywhere. Okay, you'll see it doesn't change the phases, but it changes the components at each frequency in a way that falls like 1 over nu squared. Right, the envelope of this function here, because sinc is sinc of x is sine x over x, and so it falls like sinc of nu is 1 over nu, sinc squared is 1 over nu squared. This envelope, it looks like a sine squared function that's multiplied by 1 over nu squared. Okay? So instead of this behavior, may not be as drastic as that, but the point is, it falls fast like 1 over nu squared. The envelope of the sine, which sines go up and down from 0, well, sine squared from 0 to 1, right? But the tops go down, the relative maxima at multiples of pi, integer multiples of pi, stay at 1 for sine squared, but you're dividing by nu squared. And so we're not so happy with that, because linear interpolation blurs. It throws away, or attenuates, not entirely throws away, it attenuates these higher frequencies. Okay, and you have to realize that when you're doing linear interpolation, you're having that effect. And then I talked about the fact that because we have more than one dimension, we can separately do linear interpolation in the x direction and then on the result in the y direction, so as to interpolate this position and this position in the x direction from this and this guy from this and this, where these circles are in x at the same x position as the target value position that we're after. And then we can do another interpolation between the two circles and we get the x. We can interpolate in x and then in y. Or we can interpolate in y, interpolate in y, yeah, here we go, there, and then interpolate in x. And the math shows that that's the same. Doesn't matter which order you do it, but that's how bilinear works. And in 3D, if you have a little voxel and you have some place in the middle of that, you figure out its x value and you interpolate in x in the front side and in the back side of that little box. And that gives you a place in this little square that goes through this x. And then you interpolate in, if you did it in x, now you interpolate on that result in y, and you get something along a line, and then you interpolate in z and on the result, and you get the same. That's trilinear interpolation. The same, okay? It's just saying that the convolution, which is successive, you're just cascading operations, is a multiplication in the x direction by a filter in x that goes like 1 over nu squared. Filtering the result in the y by another 1 over nu sub y squared, and then in z by 1 over nu sub z squared, right? And the overall filter effect is the multiplication in the frequency domain of all 3 of those effects. Got it? Okay, that's great. So now we have linear interpolation, and it has 2 weaknesses. The one I've been prattling on about, namely that it attenuates the higher frequencies. So, and the second is that it's not isotropic, meaning if you are interested in operations that happen, say, in diagonal directions, the interpolation is not going to be, it's sort of focusing on the x and the y and the z directions, and not on the other, and not as much on the other directions. So its effect, the effect of the interpolation, is not the same if you rotate your coordinate system by 45 degrees, for example. Okay, well, you can play the same game, but instead of just taking the box you're in, you can, for example, take so that the dots all line up. So instead of having using these 4 values in your interpolation at x, you're using these 16 values, right? Surrounding, and figure out which box the x is in, and expand it up by a factor of 2 in this direction, a factor of 2 in this direction, and likewise in x. And now we use a 4 by 4 set of input pixels to do the interpolation separably. And so each one of them is an x interpolation followed by a y interpolation in 2 dimensions, or in 3, followed by a z interpolation. And each one of these unidirectional interpolations involve 4 values. And so if you're thinking in terms of a polynomial, it has 4 coefficients if it's a cubic. And so if you do it that way, you'll have cubic interpolation in x and cubic interpolation in y. And you saw that already with the splines, the B-splines that were cubic functions, although they weren't interpolators in the sense that they didn't actually give you the value back at the original pixels. If x is on top of a pixel, an interpolator would say, at least I should keep the value there. Maybe. Well, if it's precise it should be that. But if you know there's error, then you may not want it to be exact. But for the time being, let's assume this desirability to have interpolation. Okay, so then you have bicubic, and you can play biquadratic or whatever dimension you want. But people typically don't go higher dimensions than that. They typically use bilinear or biquadratic or bicubic. And what happens when you do that is that this function that in the frequency domain, if you have bicubic, for example, it will attenuate less. It'll lower the components at higher frequencies less. It'll still blur, but it'll blur less. And that's just fine as long as the image is smooth. But images aren't typically smooth. They're piecewise smooth. In the space domain, images have nice smooth sections, and then they have an edge. And then they have nice smooth sections, and they have another edge. Okay, and so the point is that images have these significant, more or less discontinuity, sharp changes in intensity at boundaries of objects. Right? I don't care whether you're in a CT image or you're in an image with a camera, you're going to have these objects. So you do CTs, you're going to have kidneys, and you're going to have boundaries of the kidney, right? And if you're blurring, what happens here is that the sharp edges become blurred. Right? The result is, instead of falling sharply like this, it may fall like that instead. Right? The edge becomes less sharp. And that's because edges, these discontinuities, have a lot of high frequency components, have their coefficients at high frequencies, at small levels of detail, small wavelengths, are notable. And the interpolator is severely attenuating at those frequencies, meaning you don't get, you force smoothness as a result of the interpolation that you didn't want. So, since these edges are so important to us, we desirably would like to have closer to this rect behavior, this behavior in the frequency domain, this constant out to the between frequencies minus a half and plus a half. Okay, so we would like to we would like to multiply by a rect. What's the kernel in the space domain corresponding to multiplication, a transfer function of filter, which is rect? Think right on. If it's a Rect in the space domain is sync in the frequency domain. If it's a rect in the frequency domain, it's a sync in the space domain. Okay? So ideally, the kernel we would like to use is sync. It gives us a weighting function. But the weighting function goes a whole long way, right? It stops, it falls off like 1 over x in the x direction. And like 1 over y in the y direction. Okay? And that's a fairly slow fall off. So the point is that you're taking a weighted sum of pixels that are 20 pixels away in each direction. Plus or minus 20 pixels away from where you are. Right? Or you can go over in the frequency domain. And the interpolation is the application of the rect in the frequency domain, and that's great. Except, big time except. And it's this problem here. If you had a perfect edge, everything would be great. But we don't have perfect edge. All images have noise. And the effect of noise, the effect of imperfect edges, is that the edges appear in the image, something that was an edge, now appears oscillatory. It comes from the oscillations that you have in the sync function. And that produces, little bumps in the image intensities. And those bumps are pretty harmful to most of the things we want to compute on the image. If we want to just view the image, we see these extra light to dark variations. And if we want to compute, object properties, it's as if there are a whole bunch of extra edges. Yeah, they're somewhat low amplitude edges, but they're not low enough to not cause us difficulty. And so this, quote, ideal interpolator, the sync function, has this really unfortunate property from the point of view of all the operators that we want to follow on the interpolated image, that we basically can't use it. But at least it's worth understanding that what we're trying to do is find an operator that we do want fall off, because out here the signal to noise ratio is bad. In high frequencies and low frequencies in the original image, the signal to noise ratio is crummy. We've seen that. And so we would like not to keep that bad signal to noise ratio, but we would like something that more falls off like that, depending on what the signal to noise ratio is in doing our interpolation. We would like the filter to look like that and not like rect. And we can do that by combining the rect with something like a Gaussian. So instead of falling off the way I had here, it's going to fall off in the frequency domain like that. Or we can build one that's even more an aperture that's not Gaussian. But of course, we have seen the nice properties of having apertures that are Gaussian. Okay, we come to the end of this lecture. I just want to show you where we're going. First of all, I am building an assignment for the next period. Ideally, I think the assignment will be available to you next Thursday. And it will be the next to the last assignment, and it is on the combination of multi-scale notions and on this interpolation business. Okay? And as you'll see, there is more or less one lecture worth more in this interpolation section. And then we're going to switch into another topic. We are talking about these geometric operations of rotation and translation and scaling and deformation. And we're going to talk about how you do those. And then the final assignment will be on that. And there'll be one more topic area, which has to do with ridges, which ends up finding things like bar centers and edges and so on, understanding the mathematical of what's going on there. Anyway, so I will be putting up on Sakai, well, I put up this, we're going to talk about splines and especially this successive subdivision method, and then least squares next time. And then we'll be going on, and I'm putting up on Sakai the slides for, there are two sets of slides for these geometric transformations section. And you'll find both of them there. Be aware that I modified the interpolation one. There was one slide missing that was hidden in what was up till today, and this morning I put up the one that I'm actually using in lectures for the interpolation section. Okay, I really hope you feel good about your performance on the exam. You have plenty of time, but please start early, because after all, it's an open book exam, and if you don't know something, you have a chance, if you do start early, to go look it up. All the best.